Okay, so welcome to Math 349. Actually, I think this is lecture 36, not 35. So I'll just update that over there and fix that later. So what I want to do is I want to talk a little bit more about the statistics, what do you mean? And then go into some other fun topics. And so this gives an opportunity to discuss, the different ways of proving things. And as you're writing things up, you have to take into account who is your audience. So a lot of times when people write up math research papers, they use the best results possible. This actually is not necessarily the best thing to do. I like to use what is the weakest result I need to get the result that I want. And so a lot of times, I don't actually need the best known result. I just need anything greater than the following. And this gives you a sense of how deep is the result. Also, of course, depending on who you're talking to, different people have different backgrounds. And so I want to go through a couple of different proofs that have wonderful techniques. So we have the famous geometric mean, harmonic mean inequality. So GM, AM inequality. So let's say x1, x2, ... xn are greater than or equal to 0, then the arithmetic mean x1 plus xn over n is greater than or equal to the nth root of the product. So there's lots of ways to prove this. So one is Lagrange multipliers. And so I asked you to think about how might you do this using Lagrange multipliers. Now, one of the things that's extremely important is to decide which is your constraint function and which is the function you're trying to optimize. So there's two natural choices for the constraint function. Either the sum of the x's or the sum of the x's over n is one possibility, or the product of the x's or the nth root. Now, when you have something like this, note it's okay to send each xk to alpha xk for alpha greater than 0. If I rescale all the x's by alpha, the left-hand side rescales by alpha, the right-hand side rescales by alpha. So without loss of generality, I have some freedom. So without loss of generality, either x1 plus xn over n equals 1, or the product equals 1. And it just makes life a little bit easier. And depending on which way you're trying to do the algebra, sometimes one is more useful than the other. What's nice is there's only two choices. So if you choose something and it's not going well, what should you do? Choose the other one. And what if that's going even worse? Go back to the first, right? And say, oh, it wasn't so bad after all. So it's nice when there's only two possibilities. So over here, which would we rather have? All the x's multiplying to 1, or the sum of the x's dividing by n equal to 1? We can do it both ways. Now, when we do Lagrange multipliers, it's extremely important that we have a compact set. How many people here have taken real analysis? Okay, not that many. So we need the x's to live in a bounded box. Say 0 less than or equal to xk less than or equal to some big B. Then real analysis says any continuous function takes its max and minimum. Okay, so this is a big result from real analysis. How many people did Lagrange multipliers in calculus, in Calc 3? All right, so you should have hopefully seen Lagrange multipliers. But what they do is Lagrange multipliers find candidate points for maxima and minima. They're not necessarily maxima and minima. It could be a saddle point. It may not be a maximum or minimum. So for example, if I give you the function f of x is x cubed, if I try to plot this function, somehow extreme close up. I'll let Wayne's Wood. Okay. So if I try to plot this function, the function is going to look something like this. And so if f of x is x cubed, f prime of x is 3x squared, we have a critical point at x equals 0, but not a max or minimum. And the issue is f double prime of 0 is also 0. That's why things break down here. So it's not enough for the first derivative to be 0. So unfortunately, we may not actually have a maximum or minimum. A lot of times from physical grounds, you know that there has to be a maximum or minimum. If you look at all possible allocations of resources for your business, there's got to be something that's going to optimize your profit. I don't know what it is, but I'm not going to generate infinite profit. My profit is going to have this huge upper bound. Or I'm trying to schedule movies and I'm trying to maximize attendance or trying to maximize revenue. There's going to be some huge upper bound. So the question is, which is going to be easier? If I set the product equal to 1 or set the average, the sum of the x's over n equal to 1? Well, if the product is equal to 1, what can you tell me about how large things can get? So how large could xk be? Arbitrary, right? What if x1 plus xn over n equals 1? How large could xk be? At most n. I hope this gives you a sense of, if I'm doing Lagrange multipliers, which way might I want to do things? If I set the arithmetic mean equal to 1, then I have a finite box. So now I have the tuple x1 through xn lives in the interval 0, n, n copies of that. Each variable is between 0 and n. Okay, so now let's try to do Lagrange multipliers. So I've got, which is the function I'm trying to optimize? And which is the constraint? So which is the one we're trying to optimize? So the sum is what we're trying to optimize? Then that means the product is fixed. So did we want the product to be fixed or do we want the sum to be fixed? So if the product is fixed, where do the x's live? They can be anything. They live in 0 infinity. So we want the sum. So if I'm doing it like this, I would want my constraint to be x1 plus dot 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 plus xn over n, maybe minus n equals 0. I'm sorry, minus 1 equals 0. So that would be my constraint. I'm forcing the sum. And then what function would I want to optimize? Tell me what I'm optimizing. So say what the product is.
Oh, x1, x1.
So is that what we want to optimize? Is that what we had in the arithmetic mean, geometric mean? It's the nth root. Do I care about taking the nth root? Yeah, if I optimize this, then I can just take the nth root in a moment, and this will make the algebra a little bit easier, right? So just like when we would ever in calculus, if you're ever trying to minimize, say, the distance from a point to a curve, you never look at the distance. What do you always look at? So if you look at the distance, it would be like the square root of x minus a squared plus y minus b squared plus z minus c squared. You don't want to have a square root. Rather than looking at the distance, what would you look at? The square, right? So this might be a little bit easier. Take the nth root later. nth root greater. We have the following equation. The gradient of f is lambda gradient of g, and g of x1 to xn equals 0. So here we have n plus 1 equations. We have n plus 1 variables. x1 dot 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 xn and lambda. Which is the variable that you care the least about? Lambda, right? I really don't care about lambda at the end of the day. Lambda is designed to help me get to the candidates x1 through xn. But if you can generate x1 through xn without telling me what lambda is, that's fine. It might be easier to find x1 and xn by finding lambda first, but at the end of the day, I only care about the point. So the lambda is the least important. So let's look at what the equations are. So what's the gradient of f? So this is going to be df dx1 dot 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 df dxn. What do you get when you differentiate first with respect to x1 when you differentiate the product? I'm sorry? Everything except for x1. And what do you get when you differentiate with respect to x2? So you can write this, if you want, as x1 to xn, 1 over x1, 1 over x2, dot, 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 1 over xn. That's a nice way, if I have everything but x1, it's the same as everything divided by x1. And this just makes the algebra a lot easier. What's the gradient of g? So what would the gradient of g be? Yeah, everything would be 1 over n. So if you look at this, what does this suggest the answer is? So we want the gradient of f to be equal to some multiple of the gradient of g. So can you look at this and can you tell me what the x's are?
But there is no x.
So there's no x in the g's. Well, at the end of the day, we also need g of x1 through xn to be satisfied. We need that to equal 0. So we need the arithmetic mean to equal 1. What can you tell me about x1 versus x2? When you look at this, what can you tell me about x1 versus x2? What are the possible relationships between any two numbers? I'm sorry, no, because these are real numbers. So if I give you two numbers, there's 3 possible relations. x1 could be greater than x2, it could be equal to x2, it could be less than x2. Look at what we have. We have the same number outside everything in the gradient of f. We have the same number outside of everything in the gradient of g. What does the relationship between x1 and x2 have to be? Has to be equal, right? So without loss of generality, we can assume that the x's are not 0. So without loss of generality, each xk is not 0. And then we get, x1 through xn times 1 over xk equals lambda over n for all k. So all xk are equal. If you look at it, we have incredible symmetry. This vector is all ones. what another way of looking at it, instead of saying it's all ones, it's all the components are equal. So all the components of the gradient of f have to be equal. So since we need g of x1 through xn to equal 0, that implies each xk equals 1. And so do we think that this is a maximum value or a minimum value? Have extremum at x1 equals ... equals xn equals 1. Does everybody agree that all the x's have to be equal? So is it a minimum or maximum? Remember, we have each xk is in the interval 0, n. So what's the minimum value? The minimum of the product is 0, so this is a max. So x1 through xn is always going to be less than or equal to 1. So the nth root of x1 through xn will be less than or equal to 1. So the nth root will be less than or equal to the arithmetic mean. And that finishes the proof. There were a lot of really nice ideas behind this problem. There were two ways to go about it, if we're doing Lagrange multipliers. 2 is a small number, right? This is not going to overwhelm you if there are 2 possible ways to approach a problem, right? You try one, if that doesn't work, you try the other. But if we can do some logic and figure out which is going to be the better way, then we might as well try to do that. And here, you're trying to look at what was going on. We saw that if we set the product to equal 1, that could cause some issues. And so it's better for this one to set the sum to equal 1. Okay, any questions about this? A couple of other good points to remark on this is that this is giving us candidate points. We have to then go from candidate to actual. That we have this scalability. So we can always multiply by alpha. So as long as the sum is not equal to 0, we can always rescale the sum to equal 1. And that's why without loss of generality, we can say, let's assume the sum equals 1, because we can multiply all the x's by alpha and not really change anything. Okay, so let's now look at another proof. So let's go to a proof by induction. And again, I want to show some interesting ways to prove this. So we proved it using geometry lab. Okay, so again, we're trying to show the geometric mean is less than or equal to the arithmetic mean. So proof. It's clear when n equals 1 or n equals 2. We did n equals 2. So assume true for x1, xn minus 1 greater than or equal to 0. Prove true for x1, xn greater than or equal to 0. So we can assume whenever we have n objects, whenever we have n minus 1 objects, it's true. So do we want to have the sum fixed, or do we want to have the product fixed? And for this one, we're going to fix the product. Let's assume x1, x2, ... xn equals 1. What's nice about that is that I don't really have to worry about taking the nth root. So I was a little disappointed that I had to set the sum equal to 1 last time, but now I can set the product equal to 1. I want to apply induction. I have to have n objects. So if all xk equal 1, clearly the geometric mean equals the arithmetic mean, and we're done. Right? So now, oops. So now assume not all xk equal 1. And this allows me to review something from linear algebra. What must be the case if not all the xk's equal 1? What can you deduce? Therefore, there exists what? So the product is equal to 1, but not all the x's are equal to 1. What must be true? Excellent. There exists, without loss of generality, x1 greater than 1 greater than x2. I can always relabel them and make them x1 and x2. So that is the key observation here, that there's got to be something greater than 1, and if everything was greater than 1 or equal to 1, then the product would be greater than 1 since something was greater than 1. So the only way the product can equal 1 if something is greater than 1 is if there's something corresponding that's less than 1. This might be somewhat reminiscent of linear algebra when you were doing linear independence. When you're trying to write a vector as a sum, frequently there's got to be 2 non-zero elements, or it's going to just be a multiple. All right, so we know there has to be at least 2 things. So now what we can do is let's consider x1, x2 as one number, x3, x4, ... xn. How many numbers do we have? I'm sorry? N minus 1 numbers. So by induction, what do we know? We know x1, x2 plus x3 plus xn divided by something is greater than or equal to the n minus first root of x1, x2, x3 ... xn. So what do I divide by? I divide by n minus 1. And what is the right-hand side equal?
Still 1.
It's still 1. Just because I multiply x1 and x2 together first doesn't mean I change the product. So this implies that x1, x2 plus x3 plus ... plus xn is greater than or equal to n minus 1. We must show x1 plus x2 plus x3 plus xn is greater than or equal to n. Yes? No, we do not know that. We do not know that. Correct, and that one of them has to be strictly large and one of them has to be strictly smaller. Because if they were all equal to 1, then we know it's trivially true. Yeah. And so as soon as one of them is greater than 1, there has to be something that's less than 1, or the product would not equal 1. So for the rest of the x's, we don't know which ones are greater than 1, less than 1, or equal to 1. Yep. So now we have almost what we need. We have a huge amount in common between these two. So if we look at what's going on, we win if x1 plus x2 minus x1, x2 plus 1 is greater than 0, I believe. So what we're doing is, if you subtract the x3 through the xn's cancel, so you get x1 plus x2 minus this is greater than or equal to, and which is going to be a plus 1. So we move this over. And so if we can show that x1 plus x2 is greater than or equal to x1, x2 plus 1, then what we can do over here, this is really the same as x1, x2 plus 1 plus x2, I'm sorry, plus x3 plus ... plus xn is greater than or equal to n. Yes? Well, because we have to have n minus one objects. We're proving things by induction. So we're assuming we know the arithmetic mean, geometric mean inequality when we have n minus one objects. And then we're trying to show that we have it when we have n objects. So we're grouping x1 and x2 together to create this new number, x1 times x2. And now we have n minus one numbers.
And group by multiplication and not addition.
Correct, because if we group by multiplication, when we then multiply the numbers, we now have the same product as before. If we added, then we would not have the same product as before, and we couldn't say that it equals 1. So we're starting off with n numbers that multiply to 1. And what we're doing is we're grouping two of them together so we have n minus 1 numbers. And if you look at what's going on, we now have this inequality. So just moving the minus 1 over, we get x1 times x2 plus 1, plus all of this stuff is greater than or equal to n. We want to show that the sum of the x's is greater than or equal to n. Well, if x1 plus x2 is greater than or equal to x1, x2 plus 1, we know this whole thing is greater than or equal to n, so then that would mean this whole thing would be greater than or equal to n. So all we have to do is show that x1 plus x2 minus x1, x2 plus 1 is greater than or equal to 0. And if we can do that, we win. Okay, so must show x1 plus x2 minus x1, x2 minus 1 is greater than or equal to 0. And recall, we have x1 greater than 1 greater than x2. So I claim the left-hand side is x1 minus 1 times 1 minus x2. Do you believe me? Yeah, why do you believe me? FOIL, right? So if we just expand everything out, we see that this is just x1 plus x2 minus x1, x2 minus 1. What do we know about this? What do we know about x1 minus 1? Nope. I mean, x1 could be 55 quadrillion. What do we know about x1 minus 1? Positive. So this has to be greater than 0. What do we know about 1 minus x2? Why negative? It's 1 minus x2. It's also positive because we know x2 is less than 1. This is why we chose the two numbers. So we get x1 plus x2 minus x1, x2 minus 1 is greater than 0. And we win. And so this is a nice proof by induction. So we assumed it held for n minus 1 objects, and now we show that it holds for n objects. And we can just keep lather, rinse, repeat. Any questions about this? Yes.
When we first did the geometric and arithmetic means,
Yes.
it was clear that they had to be positive, but the last line, the way we grouped them, does not suggest that x1 and x2 could both be negative and be satisfied.
Which this line over here?
In the
This?
previous slide.
Right. But we're assuming all the x's are greater than or equal to 0. We don't want to take nth roots of negative numbers. So we're applying this to non-negative numbers. Okay, any questions on this? So I want to do one more proof, which is a little bit hard, but it's a non-standard proof and it's a nice proof to see. I think it's called maybe backwards induction. This is somewhat related to a colloquium talk that will be happening in the extreme near future. That for certain things in mathematics, it is much easier to work with powers of 2. And so what we're going to do is we're going to prove the arithmetic mean, geometric mean for powers of 2. What's the problem with proving it for powers of 2? Why not?
Small subset of numbers.
Yeah, very few numbers have powers of 2. So what we'll do is we'll prove it holds for powers of 2. And then once you show it holds for 2 to the n and 2 to the n plus 1 and 2 to the n plus 2, then you go backwards and say, now that I know it for 2 to the n, I'm going to show it holds for all of the n, for all the integers between 2 to the n minus 1 and 2 to the n. And then when I get it true for 2 to the n plus 2, I'll then go backwards and show that it holds for everything. So I'm going to leapfrog over numbers and just work with powers of 2. Has anybody seen fast ways to multiply matrices? If you've taken operations research with me, your hand should be up now, right? So for fast ways to multiply matrices, it's very convenient if the matrix dimension is a power of 2. And so a lot of times when we're gathering data, we actually choose to gather data in a power of 2 because it just makes things a little bit easier. If your matrix is not a power of 2 for its size, you can just append a bunch of zeros. But for a lot of things, it's really nice if you have a power of 2. So we're going to do first do for powers of 2. So we've done 2 to the 0 and 2 to the first. Okay. And I just want to check and make sure I'm going to use the same notation as the handout. I think we do n minus 1 or k minus 1. Okay. So now assume holds for n equals 2 to the k minus 1. So we have numbers x1, x2, dot, 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 x to the 2k minus 1, x to the 2k minus 1 plus 1, dot, 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 x to the 2k. And what do we want to assume that product is? Yeah, let's keep as before. Let's assume the product is equal to 1. So can anybody come up with a good way to split this as a product of 2 numbers? Because then I can use induction applied to a smaller set. Okay, but I want to write the whole product as a product of just 2 things. Well, everything less than 2 to the k, okay, then you would have unequal sizes. Yeah, so let's group all of these together, and let's group all of these together. Let's call this B1, and let's call this B2. Then what do we know about B1 plus B2 over 2? I'm sorry? It's the arithmetic mean. So what do we know about the arithmetic mean of 2 numbers? What relationship do we have? We have the arithmetic mean of B1 and B2. Okay, you're overthinking this. What are we trying to compare this to? Okay, it's close to 1. It turns out to be 1, but what is it that we're actually comparing it to?
B1 times B2.
Yeah, almost. It's not B1 times B2, it's the square root of that. And what does that equal? 1. So we know B1 plus B2 over 2 is going to be greater than or equal to 1. Why is this true? This is just, our base case. We've proven that it works when we have, power of 2. So now let's think about what we have. So if we look at this, what do we want to divide B1 and B2 by? We don't want to divide it by 2. What would you want to divide it by? Two to the k, right? We want to divide it by 2 to the k. Right now, we only have it divided by 2. Yes. Well, no, because in that case, then we have b1 plus b2 over 2 to the k is just going to be x1 plus x2 plus ... plus xn over n as n equals 2 to the k. B, right. Yes. Or the sum. So we have to figure out what do we want here. We have some freedom in terms of what we do. So right now I'm using the b's as products. And so if I try to do that, is this the case? No, this is not exactly what we have. So we have to rethink things a little bit. So what's the right way to look at this? So it was close, but it was not quite. So we have 2 sets. We have x1, x2, ... x2 k minus 1, and we have x2 k minus 1 plus 1 ... x to the 2k. So what we could do is we could look at the sum of these over 2 to the k minus 1 plus x2 to the k minus 1 plus 1 plus ... plus x2 to the k over 2 to the k minus 1. So now I have 2 numbers, right? And what would I want to multiply this by? Not 2 to the k minus 1. Not 2 to the k. We've already got a 2 to the k minus 1 in the denominator. So what would I want to multiply this by? What are we trying to get for the arithmetic mean? So we want to multiply by 2? What do I want the denominator to be? I don't want to be dividing everything by 2 to the k minus 1. So what should I multiply this by? Not 2. If I multiply by 2, then the denominator is 2 to the k minus 2. 1 over 2. This is the expression I want to study. And now maybe we can use induction on each sum, as each has 2 to the k minus 1 items. So by the inductive step, what do we know about this? That's going to be greater than or equal to the product x1, x2, x2 to the k minus 1. And then what power do we take this to? One over 2 to the k minus 1. And the other one over here, that's going to be greater than or equal to x2k minus 1 plus 1 ... x2 to the k. And we take that to the 1 over 2 to the k minus 1. So we're using induction now. What can you tell me about this product? Well, this is just the same as x1, x2 ... x to the 2 to the k to the 1 over 2 to the k minus 1. What does that equal? What does it equal? It just equals 1. And that finishes the proof. So what we did is we applied the induction to a sum of k minus 1. And it takes a little bit of time to figure out what's the way we wanted to do it. And so I initially said, let's try to do it as a product of two things and do it with B1s and B2s. But when we tried to combine them, they didn't combine properly. And so it was better to split it up and say, let's look at the arithmetic mean. And I can break it up as the arithmetic mean of the first 2 to the k minus 1 plus the arithmetic mean of the second 2 to the k minus 1, and then divide by 2. And now that I have this, that's the arithmetic mean. And so now we have the arithmetic mean is greater than or equal to 1. And without loss of generality, we can always adjust this product. So I don't even care the fact that I'm taking it to the wrong power, right? It's equal to 1. So if you want, I can drop the exponent and then put in the exponent of 1 over 2 to the k. Makes no difference because it's just 1. So there's a lot of really good ideas here. The problem is we've not proved this for all n. We've only proved this for n that are powers of 2. So now we have to fill in the remaining. So we have x1, x2, dot, 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 xn. And then I'm going to add a special number a. And let's say 2 to the k. I just want to make sure I use the same notation as I have in the handout. You can either do k minus 1 or k. I want to try to do it the same way. Okay, I want 2 to the k minus 1 is less than n is less than 2 to the k. So how many times do I have to add a? How many items do I want to have at the end of the day? 2 to the k. I start off with n objects. I've got to get up to 2 to the k objects. So how many objects do I have? 2 to the k minus n. Now the arithmetic mean is going to be x1 plus x2 plus xn plus 2 to the k minus n times a divided by 2 to the k. And what do we want this arithmetic mean to equal? So think about it. We start off with x1 through xn. We want to compare the arithmetic mean of the x's to the geometric mean of the x's. What would we love for this quantity to equal? So I really want you to get into the mindset of how do you think about what to try to prove? We need to choose a value of a so that this expression is something nice. We're trying to compare the arithmetic mean of the x's to the geometric mean of the x's. So what would you love this expression to equal? Nope. What are we trying to compare? We're trying to compare the arithmetic mean of the x's to the geometric mean of the x's. Does this look like a geometric mean? No, this is a sum. So what sum would you like this to equal? Almost. Not the sum of the x's, close. What are we trying to compare? Which means be specific. So this is a big item in mathematics. You have to use as much detail as possible. We're trying to compare the arithmetic mean of the x's. So there's n of them. So what do you think we would love this sum to equal? Not the geometric mean. The sum of the x's over n. We want this to be the arithmetic mean. Imagine we choose a so that this is now the arithmetic mean. So we want this to be x1 plus xn over n. So let's see if this is possible. So let's find a. So we would get x1 plus xn plus 2 to the k minus n times a equals 2 to the k x1 plus xn And I've got to divide by n, so I'll put n on the other side. Okay. Oh, look, notice both sides have a sum of the x's, right? So if I subtract, I get 2 to the k minus n, x1 plus xn equals n 2 to the k minus n times a. So now if I divide by 2 to the k minus n, that cancels. I can then move the n over to the other side, and I get x1 plus xn over n equals a. So this tells us if we choose a to be the arithmetic mean, then the arithmetic mean of this set of 2k numbers is the same as the arithmetic mean of the n numbers. So the arithmetic mean of the x1 through xn is the same as the arithmetic mean of the x1, xn, and then the a's. And so now we can use the geometric mean, arithmetic mean. So we know x1 plus x2 plus xn plus 2 to the k minus n times a over 2 to the k. This is just, we know is just x1 plus xn over n. That's greater than or equal to the geometric mean, x1, x2, xn. And then how many a's do we have? 2 to the k minus n to the, I'll just put it down here, is greater than or equal to x1, x2, dot, 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 xn, a to the 2 to the k minus n to the 1 over 2 to the k minus n. Okay, so now, can we show that this is greater than or equal to 1? What do you think? We're very close. We've got the arithmetic mean of the x's is greater than or equal to. But what about each a? Each a is just the arithmetic mean, right? So each a equals x1 plus xn over n. Right? So thus we get the arithmetic mean x1 plus xn over n is greater than or equal to x1 dot 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 xn to the 1 over 2 to the k minus n times a to what power? We have a to the 2 to the k minus n, and then we take the 1 over 2 to the k minus n power that. So what power of a do we get? We just get 1. And since a equals this, did I make a mistake? So I think I dropped something. Let me quickly check. Oh, we're taking it just to the 2kth root, not to the 2kth minus 9. We're just taking it to the 2kth root. There we go. So this is then going to be to the so here this is to the 2k, and then over here this is going to be 2 to the k minus n over 2 to the k. And so over here this is just a. So this is a to the first power. This is equal over here to a to the 1 minus n over 2 to the k. So I'll let you finish the algebra, but you will then get a to the n over 2 to the k is greater than or equal to x1 xn to the 1 over 2 to the k. You can now get rid of the 2 to the k's, and then you can move the n over, and there it is. So that finishes up the backwards proof. So there's a lot going on in this proof. It's worth looking at this really slowly, really carefully. I'll send out the notes later. All right, have a good rest of the day. Yes.
Oh, great, thank you so much. But I was just wondering, like,
Yes.
visually wise, when you said that you don't really like to have the frac for
Right.
numbers where there's a single like
Right.
digit, I totally get that. But when the denominator looks a little bit bigger, I mean the numerator, excuse me, that's okay.
That's okay.
And then for these, they looked really bad.
Well, are you using equation environment for that?
No, I'm just doing lines.
Right. So you need to do it. You need to put it in an equation.
Okay.
And then if you do it as an equation, then it will expand things. But when you when you do frac in a paragraph, it expands the lines, and the lines don't have equal spacing. But since you were doing induction, I wanted to do some.
See that each one of them, there was a line from like corner to corner. Yeah. And you can count the number of lines, like decimal line, and you can like figure out that there would be by definition.
So I figured, I did that as well, but I couldn't figure out, like, it doesn't scale. I think it's just like squares, like, but I don't know how.
Yes.
I was talking with Garrity yesterday because I was, getting ready to.
You don't have to explain why you talk to. He's a good person to talk to.
Of course. And he said that. Well, I was asking him about the personal statement for grad apps.
Yes.
And I was like, "Is this good enough?" And he goes, he takes up one look. He has like a couple sessions. He goes, at the end of the day, it doesn't really matter.
The only other one where I
So
You're overthinking it. It's basically like he made.
what I would say is most of the time it doesn't matter. Every now and then the personal statement can make a difference. But for the most part, I don't think it makes much of a difference. If there's something truly special, truly non-standard, this is your chance to put things in context. So one year I took somebody for small because his personal statement was, "Help, I'm an undergraduate at Cooper Union. I don't want to be an engineer. There's no math major."
and it works.
It's like, okay, you have a set of skills that would be actually useful for one of the projects I want to do.
Like if that's the right value, I'm hoping for.
And so that was one of the few times where the personal statement actually did make a difference. But most of the time, it's not a big deal what you put in the personal statement.
So I don't need to be kind of.
I wouldn't worry too much. I would make sure you have the correct school listed. I would, try to mention, a few professors that you're interested in working with.
Is it good to mention more than one?
I would try to mention more than one, because if there's only one person that you're interested in, are you really a good fit for the school? And what if that person is no longer taking students? Or what if that person is leaving? And so you don't want to be just one person.
So I'm submitting that soon, so I will send you an email saying
Yep.
the instructions for that.
Yep. And then you've got the email from me about all my personal information.
Yeah.
Yes. And then if you can wait until you do part one of the exam, I can include that. If not, don't worry, I can just write on what I've got.
Because the deadline is soon.
Yep. Yep. So it's, it's whatever it is. I try to have things as flexible as possible. Yep.
The nth derivative, the second derivative of fn should be just the sum squared, right?
Yeah.
I wrote the sum squared divided.
Oh, you should still get the like Yeah, I know. I was hoping. He's hoping I would. Yeah.
So this probably won't surprise you that I have friends who have a similar sense of humor as I do. And one year at Harvard, someone posted modified problems, and they changed them all to make them impossible. And you have a lot of people go, "Oh yeah, this isn't that bad. You just use blah, 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 blah." No, actually, you can't recreate this one. So who here has done advanced physics?
The word advanced
in no sense in advance what I said.
Right. Physics. So wait, you did physics in ninth grade?
Yeah, there was no calculus involved because my high school did physics, then chem, then 2 years of bio. So I have never seen in an actual class physics and calculus in the same context.
No, they've moved physics to ninth grade in Massachusetts, which to me is just absurd because you have people who are taking it who haven't even done algebra 2.
Yeah.
So one of the nice things is I had taken over my son and two of his friends math education, so they were doing calculus with me. Like, wow, this is so much easier to know how to differentiate and integrate.
Yeah, I think the only benefit of taking physics ninth grade is that it maybe opens up like the AP physics a little bit earlier, right?
Potentially. Right. It's just you can definitely do physics without a lot of the mathematics and talking about the intuition, how to look at things. It's just I don't necessarily trust people to do that well. And I remember I took economics as a freshman and it was a non-calculus class. And so just for some of the problems, it was just painful not to use calculus. All right, last week. All right, so I'm just seeing, so no one here has done advanced physics. So except for the fact that this is being recorded, I can basically say anything I want about advanced physics and people won't notice. All right, so let me start recording because we've got a lot to cover today. Okay.